So a short agenda today. We'll finish off this. Mainly we have A star. That's the big item. Because A star is it's kind of, you can say, the best path planning. That is on the deterministic side. Then on the random side, you have RRT, which I don't have much experience of, but maybe we'll get through a YouTube video and see how it differs. Okay, so cognition part B. So let me just recollect where we were. So the path planning world is divided into two categories. Sampling based, so RRT is in that category. It's basically, they throw out some points there, and then they try to connect it with edges. And you saw what happened in Dijkstra, right? So Dijkstra is the grandfather of all algorithms. You know, Dijkstra is considered to be the father of graph theory. So in RRT, they throw out those points into the search space, and then they connect it with edges, and then they will re-examine that based on what they find. So it's basically random in that sense. Now, you don't want to throw points behind you when the goal is here. So there is an RRT and an RRT star, and there is a random tree algorithm. So the random tree doesn't go anywhere. You know, it's just throwing points here, but the goal is there. Finally, you'll get there. So obviously, so this is how things move in academia. Somebody comes up with an idea, somebody improves it, somebody makes it even better. So that's why you have the term RRT and RRT star. So both RRT and RRT star are available in MATLAB. So those are considered the best sampling-based path planners today. But A star is considered to be the best deterministic. So deterministic means that every step is preordained. If this happens, do this. If that happens, do this. So it's like you can blindly follow it. RRT is, because you're throwing out points, the first question that arises is how many points you're going to use. So the fact that you're sampling a space should make it faster, because you don't need to put as many. See, remember I told you, like in A star, each one of these squares is going to be a cell. But you don't have to do that with RRT, because you're throwing it out in front of you, and they're all over the place. So you end up with fewer cells. So the graph created on that basis is more easily searchable. But the question is, how many points do you throw there? Because if you throw too few, you will not get the optimal path. If you throw too many, you're going to make the algorithm as computationally intensive as the first category. So if you're going to use a sampling method, you better be careful about exactly how to figure out how many points to use. Otherwise, you might as well do the deterministic approach. So we did Dijkstra. Dijkstra finds a path between the starting cell and all the cells in the network. So in Dijkstra, you don't have to have cells like this. They could be cities, you know, like Chennai, Vellore, Bangalore, Vijayawada. So you could be trying to find a path, that's the shortest path. But it can be cells. And in most robotics applications, we do use cells because it's easy. Because remember, this has to be connected with the mapping method. And the easiest form of mapping is to divide the world into square cells and see whether it's occupied or not, right? Now you do realize that if part of the cell is covered, you're going to block out the whole thing. That is a danger of the cell-based approach. Because if part of a cell is occupied, the smallest unit is a cell. So the safest thing for you to do is block the entire cell. So you're going to block off big parts of the environment, because it's either or. You know, you can't say block off part of the cell, because part of the cell does not exist. The smallest unit is the cell. So you have to pick the cell size in a way that's connected to the size of the robot. So typically the robot size and the cell size are approximately the same. I think we went through this. Did I talk about this road structure? So you have this road structure, and I only presented this method because everybody can relate to it. If we have to go around buildings to the other side of the campus, this is how we would do it. There will be many ways of going around it, and of all these roadways, you know, so you form artificial roads. You can't have a road go through the building, because the assumption is that you can't go through the building. If you can go through the building, you have to split the building into two parts then. But right now we assume that you can't go through the building, the doors are locked. So of all the roadways, you know, you see here is a very long one. This is the best. You can tell using your human intelligence that is the best method. So graph search algorithm, Dijkstra can do that. Once you have the roads, Dijkstra can figure out that this is the best path. We discussed the potential feeds method. So And I also talked about, how people get scared of the word optimal, but there's no such thing as optimal in the real world. Optimal is based on the assumptions of the derivation. So you can have a suboptimal solution that actually works better than the optimal. So if the optimal takes 2 hours to, I'm just exaggerating here, but if an optimal path takes 2 hours to compute, then what is the robot going to do during that period? Sit around and wait, because you could be having shells lobbed at you on the battlefield. So it's useless. That particular optimal solution is useless at that point. You have to look for a suboptimal solution because you don't want to get destroyed. So it's probably better to move on a suboptimal path rather than sit here and wait for the optimal path. Okay, so let's move on to A star. Now, the way I did it for the other group, and it seemed to work, is I showed them what A star can do. So this is a YouTube video by Sebastian Thrun, who is the father of the first self-driving car in the world, the Google car. So that's what you'll see first, and then everything else will fall into place after that. This is actually quite a nice video, so I want you to see all of it. Go.
So here's an actual implementation of the Darker Urban Challenge, the Stanford car, trying to find a way to a maze, and as you can see, the maze is changing.
So what's happening? The whole map is not available. So as the car moves forward, you're seeing more and more walls, right? And you have to adjust. This is the real world situation. So even with Google Maps, it's not a perfect map. Because if you have an accident on the road, and the road is entirely blocked. In the US, when somebody dies or is seriously hurt, they have to take a report for legal purposes. So they stop the whole traffic for maybe 1.5 hours. So those things are not on the Google map. So here, in a typical military application, anything beyond the sensor horizon, like when you turn on your power, you'll be able to see, if you have a LiDAR 80 meters, that means you can see up to 80 meters. But beyond that, the assumption is that it's empty. So your A star will draw a piecewise linear, around obstacles to the horizon. After that, since it's empty, it'll just draw a straight line. The goal could be 10 miles away, but beyond the sensor horizon, it's going to connect it with a straight line. And that straight line has to be resolved as you move forward, because as you move forward, you'll see more and more, and that straight line will go. So that's what you're seeing here. This is a very sophisticated implementation of A star. He's got a regular car, not a differentially steered robot. So a regular car cannot, a differentially steered robot can turn in place. You saw that already, turn in place and go this way. This can't. And yet he's able to use A star. As he moves, you'll see more and more walls, and ultimately he'll end up with a, goal here. So you can see these are all trial paths. And then as the wall shows up, the path will change. So the blue is the projected path. This he is already covered, right? Blue is projected path. And that blue line will be constantly shifting and changing in terms of its confidence.
As the car moves, it reflects this one effect. The car uses sensors to see obstacles. And obstacles are sometimes
so it's going to be blocked right now.
You can't only see them when they're nearby.
Dead.
What's really remarkable here is that the car is able to plan really complex maneuvers to the goal. At any point in time, you can see its best guess to a path to the goal. And the orange
you actually reverse that.
Are A star search trees. They aren't exactly grid trees. Our car moves differently.
Notice something. The extra will search the entire space. A star, because of something known as the heuristic, which we'll talk about now, is only going to search in that narrow corridor from the robot's current position to the goal. So when it encounters an obstacle, obviously you can't stick to that anymore. Then it will start spreading out. The extra is always going all over the place. A star only spreads out if there's obstacles. And that's why A star is much more efficient.
From a grid-based robot, it can turn at different angles.
It's actually reversing.
Each of these little steps is a different turning angle combined with a different forward motion. But leaving this aside, you get these amazing trees that find paths all the way to the goal using A star. This implementation is so fast that it can plan these paths in less than 10 milliseconds for any location in this maze. That was faster than any other driving team that I know of at the DARPA Grand Challenge or the DARPA Urban Challenge. The planning is repeated every time the robot cancels the previous plan. You can see additional adjustments in place at times. But as you go through this video, you can see how A star planning with a simple Euclidean distance heuristic is able to find a path to the goal. When you implement this yourself, the big difference to our grid implementation is a different motion model. You have to implement a robot that is able to turn, and you have to write on the math of a robot that's able to turn and go forward. This robot also can revert, so going backwards is a discrete different action. But other than that, it's essentially the same A-star algorithm you just implemented. So if you want to build a self-driving car, you don't understand to make a really complex, nice search algorithm to find a path to a goal. So this is a scene where DARPA tracked our car using a barrier that went all across the street. So the only way for the car to navigate this was to take a multi-pole U-turn, and it had to plan this all by itself using A-star planning. The car pulls up to the barrier, realizes there's no path to go, then invokes its A-star planner and comes up with a turnaround maneuver that is not particularly elegant, but it's super effective. And the car was able, in this competition, by itself, to turn around using A-star, find the optimal plan to do so, and move on. Otherwise, it would have been stuck forever behind this obstacle. In this final video, I show you a parking situation where the car has to back into a parking space between two other cars. And you can see how the obstacles are visible, how these other cars are visible, and how our vehicle Junior navigates an actual parking lot. Again, this is using A-star. It finds its way optimally into this parking spot, backs in and backs out again, all by itself. The planning time for each of these A-star runs is less than 10 milliseconds. And the car was able to competently do this, even though in advance they had no clue where the obstacles were and where the parking spot was. That is A-star for forward path planning. And what you've implemented yourself is the core of it. Again, if you want to turn it into a real robotic motion algorithm, you have to change the motion model, and you have to see the next class I'm teaching you when I go to continuous values and show how to turn this into a continuous motion path.
So that's A-star in actual action with the real car. These are support, because as I said, sometimes you get multiple people explaining it and one of them clicks more than others, That's how a brain is configured, Sometimes a different explanation works for you, but it doesn't work for your friend. So that's the real world. So number 3, and then we move on to the last topic, sensing and perception. So number 3. So Professor Thrun, Dr. Thrun mentioned heuristics. You'll see what that is.
Welcome to this video on pathfinding. So in this one,
so you know what you're seeing here? There is something known as a heuristic. And the heuristic, unlike Dijkstra, right? See, Dijkstra gives you the path from the starting cell to every other cell. Whether you like it or not, you cannot say I'm only interested in this one. It fans out, and you can stop when that cell of interest, its shortest path has been found. But typically it goes all the way and gives you the path to every destination. Now, where would this be useful? So for instance, in video gaming, right? So maybe the hero is eventually going to go to different spots in the environment. Maybe he's going to fight somebody here, and there's a second villain there. So then it's better for you to find all the paths, right away. Maybe based on the choice of the game player, you pick on a villain. You know what I'm saying? So then you have to have a path here, a path there, a path there. So Dijkstra makes sense there. A-star is point to point. And that makes more sense for a robot on the battlefield where you're only interested in that one destination. If you want to change and have a new destination added, you got to do it again. So essentially, wherever the robot is, you got to say, give me a new plan. I changed my mind, I need to go here now. The problem at Dijkstra, because it finds a path to all the cells in the environment, is that the execution time is related to the square of the number of cells. So when the execution time is related to the square of the number of cells, imagine if I had a 10 by 10 space, right? So square of the cells is 10 squared, 100. And I go to a 20 by 20. It's not just 2 times. 20 times 20 is 400. It's 4 times. So it exponentially grows. So at some point you find Dijkstra is taking so much computer time, you'll have to sit and wait for the paths to be generated. Whereas A-star because it's using a heuristic. In other words, it's going to direct the search directly there. That's what you're seeing here. You see here, the red here, these are all the cells opened up for exploration. You know, Dijkstra also looks at cities, right? It compares which is the shortest distance, and then it says, okay, this is explored. And then from here it tries to, look at all the neighboring cities. Well, here, because you're using the heuristic, only the reds are explored until it gets to the goal.
First episode, we're going to be taking a look at how the
See
A-star
how
actually works.
A-star just spreads here. It leaves all the whites.
Programming actually in the future episodes.
All of those are not explored.
We've got a pretty good understanding of why it works.
So you see that? It's only going to, because of the heuristic, it's only going to explore forward till barrier is encountered. Then it will spread along like water. It's going to spread this way and come around it. So.
And where we're going.
Now, why did that happen? Why more reds? Is because you have a lot of obstacles. So it's kind of forced to, spread out. So you can't create an environment where you put so many obstacles that basically Dijkstra and A-star, expend the same amount. But most of the time you won't have an, environment like that. Most of the time there's going to be openings and you're only interested in going to one cell. So Dijkstra is actually a waste unless, as I said, you want to create paths to many destinations.
Alright, so here we have a grid of nodes, the white nodes representing the walkable areas in our map, and the black nodes representing the obstacles. So, of course, we're trying to find the shortest path from node A to node B. And what we need to do first is decide how far apart the nodes are. So it would be quite natural to say that the distance between two nodes is 1, and therefore by Pythagoras the distance diagonally is going to be the square root of 2, which is approximately 1.4. So,
So, diagonal is square root of 2, right? So, these are all gamers. They don't like fractions and so on, because in the old days, the microcontrollers didn't have much power. So instead of using 1 and square root of 2, they make it 10 times so that it becomes an integer. So they're able to get away with integer arithmetic, adding integers, that kind of thing. You get the same path. If you multiply everything by 10, the path is not going to change.
What a common practice is just to multiply those two numbers by 10, and to use the nice integer values of 10 across and vertically, and 14 for the diagonals. Alright, so I've removed the obstacles for a moment so we can see how the algorithm.
So you definitely remove the obstacles to make a point.
So the algorithm begins by going to the starting node A over here, and looking at all of its surrounding nodes and calculating some values for each of them. So the values in the...
So this is the key to the algorithm. So he's going to come up with 3 numbers, okay, and F, G and H. So G is the moment cost from this node to that node. So 14, 10, 14, very routine, right? 28, right? So this is the total cost. 28 is the cost of the heuristic. So the heuristic is the Euclidean distance directly from that cell to the goal. So that Euclidean distance should really be calculated as square root of x2 minus x1 squared plus y2 minus y1 squared. But again, gamers don't like those kind of computations because it slows down. So what they do is they use what is known as the Manhattan distance or city block distance. So that means, well, Manhattan comes from New York. So if you have to go 5 blocks this way and 6 blocks this way, right? You cannot calculate the Euclidean distance because you'll have to go through buildings, right? So typically Manhattan distance is 5 plus 6, 11. Easy to compute, and it's as good as Euclidean. It still gives you the best path.
The top left corner of each node are called the nodes G cost, and that is quite simply how far away that node is from the starting node. So this node in the top left corner has got a G cost of 14, since it's just one diagonal move away from node A. In the top right corner of each node is the node's H cost, which is basically the opposite of G cost. It's how far away the node is from the end node. So this node is 2 diagonal moves away from the end node, so it's got a H cost of 28. Now the big number is the node's F cost, and that is very simply G cost plus H cost. So now the algorithm is going to look at all of these nodes and it's going to choose the one with.
So from here, right? So he's using like a compromise between Euclidean and city block. Some other gamers just go city block all the time. So for instance, some gamers for this will say 10, 20, 30, 40. He doesn't do that. He says 14 plus 14. Still no calculations, right? Because there's no square rooting and all that. So over here, so some gamers will say Manhattan distance, nothing else. So 10, 20, 30, 40, 50. Here he says 14, 28, 10. So it's kind of a compromise, but he's still not calculating the square root. So the whole idea is that with these three numbers, you ask, once you have filled out this, right, for all the cells around the starting node, you will ask yourself, which is the next cell, which is the next best cell to put on the path? And the answer is the one with the lowest F cost. In Dijkstra, there was no F cost. It was all G, because there was no heuristic. But here, it's the lowest F cost. So therefore, this one, 42, all of them are higher, right? That's what it's going to put on the path.
Lowest F cost to look at first.
Oh yeah,
And that is of course this 42 in the top left corner. So
the point is that if there are no obstacles, this will turn out to be the final cost, right? And you just go straight. But if you have some obstacles, then you go along it. He's going to put back the obstacles as the next step. He's just showing you how it would work if the terrain were completely empty.
So we'll mark this now as closed, so it will appear red. And it will then calculate all of these values again for all of its surrounding nodes. And it's quite simple to see what's happening here. These F costs are just staying the same as it moves towards the target because the G costs, the movement costs are increasing and the H costs are decreasing, and they're just sort of balancing each other out. So it basically explores the path straight to the end.
Notice, the same problem we are giving to Dijkstra, it will investigate all these cells. And so it's going to spend a lot of time. That's why order of n squared, right? Dijkstra is computationally, very intensive.
Well, no point having pathfinding in your game if you're not going to have any obstacles. So let's add those back in and run through the algorithm once more and see what happens. So once again, we look at all of the surrounding nodes and calculate their F costs. And we'll go with this lowest F cost of 42. And now we have a scenario where we have three nodes, each with an equal F cost of 48. And so what we'll do to sort of decide which
one... You can break a tie randomly.
We'll look at which one is closest to the node. In other words, which one has the lowest H cost. This has an H cost of 38. This is also 38. And this one's 24, so we'll go with this one. Now, as you can see...
So basically he made up a part of it because, the original A star, you can change it if you want to. He says there is a tie, and which one will I pick? He says the one here has the lowest H cost compared to the other two 48s. So that tells me I'm a little bit closer to the goal, and therefore he says I'm going to break the tie by picking that one. So those little changes you can make in your algorithm.
See, the F costs are increasing each time, since we're not going in a straight line towards the end. So even though the H costs are decreasing by a little bit each time, the G costs are increasing by even more, resulting in a more expensive path. So now the two nodes with the lowest F cost on the map are these two 48s over here. They've got the same H cost, so we can pretty much choose one at random. Let's go for this one over here. And now we have to look at the other one. And at this point, the most sort of promising node, as it were, is this 54 over here, and we explore that. So now we'll look at this other node with an F cost of 54. But one thing I'd like to draw your attention to quickly is the node just to the left of it with an F cost of 68. If we look at its G cost, it is currently 38. But if we look how far away it is actually from node A, it's just 10, 20, 30 away. So obviously this has come on a path something like diagonally up here, 14, then across for 24, and and then down diagonally to make 38. So as we explore this 54 over here and explore all of its surrounding nodes, you'll see how this 68 updates to reflect the new best path to this node. So it now has an F cost of 60, and it is the most promising node on the map, so we'll explore that. And now we have a bunch of 62s to look at. Not much to say in the way of commentary here, just exploring all of these lowest F costs. Until now we can come back to the 68, and we explore that. And we get to explore the other 68.
It's creeping around the
And now
obstacle.
we'll observe the same effect that we saw in the first example, where we've just got a straight line to the end node, and the G costs and the H costs, we've got to balance each other out, and the F costs won't change, and we'll just go straight to the end.
So basically, it did most of the cells here because the obstacles were so strategically placed that it was forced to fan out. So it almost became like a Dijkstra thing in terms of number of cells explored. So it essentially explored all but a few white cells here. Dijkstra would have explored all of them. So this is available in MATLAB. You
So
can run
you
it.
can see how this is guaranteed to find the shortest path, since as soon as you're not moving in a straight line towards the end, the F costs are going to increase, and then it will start looking at the other potential options. Let's look at one final example. In this case, I have hidden the G costs and the H costs, and I'm instead showing these little arrows which are basically indicating where these nodes have come from. So when we explore this 58 over here, you can see all of its surrounding nodes are now pointing to reflect that they sort of originated.
Let's remove the G and H for clarity.
Of course, there's 64 and there's 58 over here. Even though they are, its neighbors have not updated to show that they're coming from this node, since it would be a worse path. In other words, it would have a higher F cost if we were to get to, say, this node over here by going diagonally up and then down. So it will only update if it is in fact a better path that's being offered. So we continue by looking at this 58, and that yields the 66, so we go back to the 58 at the beginning. And now once again, just to demonstrate this, you can see the 66 is coming on the sort of slower diagonal path, so it'll be much quicker to just go horizontally across. So as we explore this 58 and look at all of its surrounding nodes, that node is going to update to reflect that. And as you can imagine, it just goes straight to the end now. So the point of these arrows, of course, is just that now that we've reached the end node, we can sort of retrace our steps and find the path that we took to get there.
So last word on this. So typically you won't have an environment like this where the Dijkstra is closed but still worse in terms of computation. Imagine 100 meter by 100 meter area. So then Dijkstra is going to go to all the, let's say you have 1 meter cells, right? That's 100 times 100, which is 1 times 10 to the 4, 10,000. It's going to explore all the 10,000 in the process of sorting it. But A star, because typically you won't have environments that are completely blocked, right? There's going to be gaps in the middle. So there's gaps in the middle, it's going to squeeze through. A star will squeeze through. Dijkstra will spread out and explore the whole world. So, but A star is point to point. Dijkstra is initial cell to everything. So if you have that kind of a problem, then you might as well choose Dijkstra. Okay, so let's move on to the last topic. Let me see if there's anything else of interest that can be shown. And then I guess not. These are all. I provide additional references for the students so that they can look at a different viewpoint, but we've seen it all. So let's move to the last topic, sensing and perception. I believe I uploaded that. You see, yeah. So first we go to the PowerPoint labeled robot sensing. That is like, it sets up the discussion. So here it is. So these are the common robot sensors. We only talked about a couple of them, maybe 3. So you saw a picture of the disc with patterns on it, which is the basis for odometry. So when the wheel spins, it also spins, and it cuts off light. And if you measure the pulses, you can get an idea of position as well as speed. So then you have LiDAR and ultrasound. They fall in the same category, though ultrasound is like a poor cousin. Ultrasound is like in the tens of dollars. LiDAR costs hundreds, maybe thousands of dollars. So, and the reason is this. So ultrasound, you cannot tell where in this arc, and this is sometimes 30-35 degrees, right? You can't tell where the obstacle is. It can be anywhere, right? Whereas LiDAR, the one mounted on the Turtlebot 3, has a 1 degree spacing between rays, and there are 360 degree rays all around. So it's like this, much narrower. Now, of course, if you extrapolate this, even 1 degree, two rays 1 degree apart can have a lot of spacing, right? So LiDAR becomes less certain the further out you go, and you can have LiDARs going up to 80 meters. So you can imagine, out there, you won't know whether the barrel is here or here, but in close, there's no uncertainty. So the LiDAR is, much more expensive for other reasons also, which we will talk about shortly. So we didn't talk about the GPS, we know what it is. We didn't talk about the gyroscope. So the gyroscope, remember I told you that getting theta is the biggest problem in mapping, because even if theta is off by a little bit, you're actually here, but you think you're here, you're going to place whatever you see here. And then there's going to be a problem, because you're going to be putting things all around the map, and before you know it, the map will mean nothing to you. So turn, you cannot lose the turn. So sometimes they add a gyroscope. You can also use a compass, but a gyroscope is, compass measures the Earth's magnetic field. Gyroscope measures the angular rotation rate. So similar to the accelerometer, if you integrate it once, you will get the angle. So it's only reliable in the short term, just like odometry. You can't use it for long, right? But you can Kalman filter that result with some other sensor providing you angle also. So it becomes better. So it's a method of boosting turn angle estimates by using two sensors. So you can have a gyroscope also on your robot. Now, of course, the cost is going up. The more sensors you put, but if mapping is essential, you have to do it. Because if you can't get this angle right, the map is going to be useless. You might as well throw it away. Okay, we already talked about accelerometers in the earlier lectures. Force is also available because F is equal to ma, so if you know acceleration, you also know forces in the different directions. And now it gets a little bit more complicated, because now you have a sensor which is not a new sensor by itself, but it has some of the earlier sensors. Accelerometer, 3-axis, for the 3 different directions. Gyroscope, because now the body is in space, there are 3 rotation rates, right? So maybe a 3-axis gyroscope, and then a magnetometer. It's optional because this and this are probably giving you the same information, but if you want to Kalman filter them, then they also mount a magnetometer then on it. Okay, they measure the Earth's magnetic fields. So because of that, if you have a big mass of iron near the robot, it is subject to interference. So you have to be careful about that. And calibration is also needed to get the compass to read correctly. So that heading is so important in robotics, because otherwise the map is useless. And then you have various cameras, which are like, it could be optical, that is the standard camera. Your cell phone camera is optical. It can also be infrared, where it picks up the body's heat signature. Body or even objects or animals, it can pick up the heat signature, and therefore you can get an idea of what's out there. Okay, now we have hybrid sensing systems. So these are very expensive. The INS, so INS is not the same as IMU. IMU is just a raw sensor suite. INS does something more with it, because it has built-in sensor fusion. So many people want a ready-made solution. They don't want to do Kalman filtering because they don't understand what it is. So this unit is a system, not an individual sensor, but a system of sensors with software built in, so that sensor fusion is already done. IMU plus GPS, so the GPS can, they have a input port for the GPS. If you send that in, they will Kalman filter it and give you the result. And then there's something even more sophisticated. You have something known as an attitude heading reference system. I believe all boats and planes carry this, because here's what it says. An inertial navigation system is a navigation device that uses the computer, motion sensors, and rotation sensors to continuously calculate the position, the orientation, velocity of a moving object without the need for external references. So it gives you the complete solution. And I believe every boat has it. I don't know whether our fishermen here have it yet. They probably do by now. But in the old days, they would just navigate by looking at landmarks on the shore. And when there's bad weather, that's very risky because you might not even be able to see the shore. So in the US, it's mandatory. A certain category of boat has to carry these devices. Particularly when you're commercial and you're taking other passengers, you have to have one of these, no matter how costly it is. And it costs, tens of thousands of dollars. Okay, so a lot of reference links in case you want to know more about these sensors. But now we're going to move to a different document, and that is, you've seen his name before. We used his odometry notes, and now we're going to use the sensor notes. So you don't have to go to the link because I also downloaded his notes and posted it. It has the name E190Q dash sensors. So we can't do all of these because there's too many slides here, but we're going to do the most important parts of it. Okay? So this is the classic robot motion diagram. This is what the robot is doing over and over again. So the first thing, no matter what your mission is, you have to get this going. That based on a map, you localize, and then based on localization, your brain tells you, hey, I'm supposed to be there, I'm not yet there. So it gives commands to the robot to move it in the right direction. So you can't move it in the right direction without knowing where you are first, right? So first localize, and then it moves the robot, and then when it moves, remember the looking up and the counting steps? So basically, you again figure out through Kalman filtering or any other method that you want to use where you are, and you do it over and over and over again. So every mobile robot is doing this multiple times, like it's in a loop. And then you're doing other things, on top of it. Like if you're looking for somebody whose face you should recognize, that is happening on top of this. This is always necessary. But then on top of that, if you're trying to find somebody in a crowd, then you add face recognition, and that's also going in a loop. So this is a robot from many years ago, probably 3 or 4 decades ago. You can see it has everything. It has an omnidirectional camera up here. Omnidirectional means it can, see all around it. That's why it's mounted to the highest point, because if you mount it lower, then other parts of the robot are going to block it. And there's also a pan-tilt camera, that's, this and this. So pan-tilt camera, sonar sensors right here. Laser rangefinder, look at the laser rangefinder. That is like, I would say 6 or 7 times bigger than today's laser rangefinder. This is one of the earliest rangefinders. At that time, they used to cost $3,000 or $4,000. A bumper, so he's also using a physical bumper as the last resort to stop. And then IMU, which is the inertial measurement unit, emergency stop button. All of these things have an emergency stop button because they can seriously hurt somebody. And then wheel recorders, which you can't see, but it's somewhere here. Okay, so we'll go through only some of these slides. So this terminology is kind of interesting. Sensors are divided into 2 categories, proprioceptive and exteroceptive. Now, proprioceptive, people say, what the heck is that? Extero. So sensors that are looking out at the world, they belong to this category, exteroceptive. So obviously the other one by default represents sensors looking internally. So the odometry is looking internally, because when you count your own steps, you're not looking outside, right? So the odometry belongs in this category, IMU belongs in this category. If you have a speed measurement, that's also proprioceptive. Heading is also proprioceptive, and so on. So LiDAR belongs to exteroceptive. Cameras, exteroceptive. So he's using this to motivate his students, so this picture keeps showing up. You also have this categorization of passive and active sensors. So LiDAR is active sensor because you're throwing energy out there and collecting the returns, right? Ultrasound, same thing. You're throwing energy, collecting the returns. Camera, no energy. So camera is not an active sensor, it's a passive sensor. So that's this categorization. So on that, so again, the same picture. On that basis, he lists a number of common robot sensors and he puts them in the category of proprioceptive or exteroceptive. See? PC, 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 and then active or passive. So bumper is obviously passive. There's no energy involved there. You get the idea? So essentially, that's what it is. Here is internometers that, so it can measure. If the robot goes on a ramp, it can tell you what is the angle of the ramp. So even when you're moving on 2D, you might allow yourself going up or down a ramp, and that information might be useful for you to navigate. So you can have, depending on the type of sensor, you can have active or passive. That's what it means by that, A/2. So it goes on and on. There's many of them. Vision-based, speed. So here comes the ultrasonic sensor and the laser rangefinder. They're both exteroceptive and they're active sensors. So it's kind of nice to know. It's kind of nice to break down the world of, or the family of sensors into subfamilies. Okay, now, this is interesting because essentially, see, the infrared sensor, right, has a range of 10 to 80 centimeters. Now, you're saying, why 10? Why doesn't it start at 0, right? Now, the reason is, when you are getting energy, right, from somewhere, it takes a certain amount of time to process it. So, that's why close-in distances are blocked off. Because no matter how fast a processor you put, because of the technology of that time, maybe now if you put a brand new microcontroller, you can make the 10 centimeters into 5 centimeters. You cannot make it 0 centimeters. It's not possible because it takes time to process the return, right? So 10 to 80 centimeters. The one on the turtle board, the LiDAR also has a limit. I don't remember what it is. I believe it was 5 centimeters. So if somebody sneaks in from here, you won't see it. But of course, if somebody is coming in from here, you've already seen that, right? And so you can react to it before it gets within 5 centimeters. But if somebody comes from here, from the side, you won't see it because they get into within that inner number. But if they're coming from here, how can they get to 5 without first doing 20, 15, 10, right? So you'll see them and you'll be able to do something about it. We won't go through this, this is common stuff in anytime you are thinking of buying a sensor, you go through the data sheets and all of these are explained, and sometimes they won't make any sense and you have to call the manufacturer and ask, what do you mean by, this kind of error, this type of error, what does it really mean? Yeah, you have to get them to describe it for you. Okay, somewhere here, I wanted to point out why LiDAR is so expensive. Maybe I bypassed it, but maybe not. But let me just make sure I haven't skipped past it. No, I haven't. So it must be ahead. So sensors in the real world, as opposed to sensors in gazebo, right? There will be a phenomena whereby it's giving you errors, which could be one of two categories: random or systematic. So systematic means you can repeat the experiment and you will get it. So you can predict, oh yeah, I'm going to get a systematic error in this situation. And therefore, because it's systematic, you can take action in software to deal with it. Random error is the more sneaky type of error. It means it can happen and then you can't recreate the situation. So for instance, identifying lane lines, right? On a particular day, you might have such a bright sun. So bright conditions are the worst for image processing. If it's cloudy, you don't get glare, it's the best. So also you have this problem when you're doing image processing. Early morning and late evening, if the cameras are facing the sun, and this is true for us also, we can't keep our eyes open if we're staring into the sun. So early morning and late evening, you will have problems with image processing. So random errors are those that creep up sometimes and you can't even recreate the situation, you can't reproduce them. And therefore they are the ones that are most difficult to deal with because you can't even recreate them. So how are you going to fix them or you might not be able to fix them, but you may want to take evasive action, right? You might want to avoid looking into the sun, for instance. So random errors are the toughest for you to handle. So basically, remember the Gallon filtering discussion? The uncertainty of the measurement is, you use a Gaussian or you can use some other probability distribution, but essentially that's how you have to model it because it's not certain. No sensor is certain. And the people who make the sensors themselves will tell you that it's not possible to have perfection or certainty. So this is standard, it's not so much robotic stuff as it is standard sensor stuff. So I wanted to show you the encoder stuff. That's where we're going. because this was the encoder we originally used the picture of. But look at how complicated it can get. See? 3 channels. You know why? Because they are reading it off in a digital fashion. Remember I said pulse, count the pulses? That is very crude. Now you can actually read the pattern. So, 101, right? That tells you where the wheel is. So it becomes much easier to calculate rather than counting the pulse. So that's why they have these sophisticated patterns around the wheel now. It's all printed, laser printed. Nobody's sitting and painting alternate black and white, like painting black squares next to white areas. So it gets, look at this. I don't even know what that is, but it has so many channels. Of course, if you use one of these, then there's going to be a heavy burden on your microcontroller. So buy it only if you're going to use it. Don't put one of these and then say, okay, I'm only going to use one channel, right? Because you paid a lot of money and you're not using its capabilities. Obviously, it's quite sophisticated. So sometimes they gray code that. If you remember a digital logic class, you remember what gray code is, but we're not going to go into that. And essentially, I think we'll finish this. Now, the last piece is probably the most interesting, and that is the perception. So let's look at the second document, perception. And here there'll be a connection to VIT because you'll see 3 of the students who I recruited with the help of my colleagues here, and they all got their PhDs last year. The last one was Kartika, and they are now gainfully applied, doing well. And I just wanted to show you their pictures. That will come after we discuss. So I find this Huff transform really interesting, and I hope you do too. If any good at explaining this. So here's what the Huff transform is supposed to do. So any line structure, you see here, right? So by the way, how do we pick up objects in an environment? It's because of the contrast. If everything had the same color, right, I would not be able to tell that there are 4 students there. It's because I can tell that from light and shade that, there is a difference, right? That's how we pick up the outlines of objects, by the way. As we grow up and we are babies, we pick up and, recognize a dog and so on because of the contrast. Now, computer programs can do that by means of a technique known as edge detection. So what you do is you first convert the color image into a gray level image. So gray level will have different shades of gray, and then you convert that into a black and white image. And then this technique of edge detection, it basically goes across the image looking for spatial change, not time change, but spatial derivative. So anytime there's a spatial change, that will happen over here, as you come across here, right? It'll happen there, it'll happen here, it'll happen here. Similarly, look at this. That is a line, right? You may not think of it as a line, but the tree top is a line. Look at the contrast. So this Huff transform technique will pick out all straight line structures. And then it's for you to find the ones of interest to you. Now, you are not interested in the top of the tree line because your car is not going to drive there. You are interested in knowing these edges most importantly. And you can, from all the lines it picks out, the Huff transform technique, you can use heuristics, common sense rules. You can say, okay, I'm on this road. I know the width of the road is, maybe 5 meters. So what lines that it has picked out for me, the Huff transform algorithm, is spaced roughly 5 meters apart and is heading in the direction of, where my car is going. Because you don't expect the lane line to suddenly be here, right? Unless your car got into an accident. So with the Huff transform with the addition of heuristics is a very powerful tool, as you'll see. So the beauty of Huff transforms is that in the real world, you're not going to find a continuous line of pixels. There will be pieces that are missing. Maybe the cement has come out, right? Maybe out here there's my mouse. So maybe there's a pothole here. So if there's a pothole here, when you do edge detection, you will get a spike because the pothole will be a different color from the main road surface. But you have to use common sense, and then you can exclude those potholes, and you still end up with the main ones, the main edges. So look at this. This is an old style European building. Look at the number of features it has pulled out. All these whites, it has pulled out the window edges, the rooftop line. So that's what half transform can do. It's a very powerful technique. Now how does it work? Let's see. I told you this, contrast is used to determine the edge pixels. So I have this habit of talking ahead of my slides, which I should correct. So this is the main part, okay? So listen carefully. So any line, right? So we're talking in the image plane now. The image plane is physical space. So any line can be represented by y equals mx plus c, right? And we are looking for all these lines, treetop lines, right edge of the road, left edge of the road, yellow line down the middle of the road. All of these are lines, right? So if you take any one of those lines, it has a single MNC, correct? And therefore, if you go to a different plane, C versus M, so C versus M, right? It will be only 1 point, because all of these have the same slope and intercept. So a line will map to a point on the MC space, right? And then the question is, how would a point XA, YA in XY space, like suppose you just take a point, the whole line mapped to this, right? A point here could have any MNC, because you can have a line this way, this way, this way, this way. So you can have any number of lines, right? Are you with me so far? The entire line maps to a point, but if you just take a point on the line, it can have any number of MNC combinations, because you can pass any number of lines through it. So here's how Huff works. It's going to get every pixel in the image vote. Each pixel gets a vote. It's going to say, I'm on this line, I'm on this line, I'm on this line, right? So we just now said that a point here or a pixel. So by the way, in images, right, there's no such thing as a point. The pixel is the minimum, element, right? Like 512 by 512. Nowadays we have 4K, and your new iPhones are really, lots of resolution. So each one of them gets a vote. But don't you think the most votes are going to be collected by the MNC, which is part of a line structure? All the others will say, I'm on that line, this line, this line. But the ones that consistently vote for the same MNC will be the ones on all the straight lines. They will get the highest votes. So when you do a Huff transform, right, you can pick, okay, which MNC got the highest vote? Okay, that's my strongest line. Which MNC got the next vote? That's my second strongest line. Because not all lines will be equally strong. Some will be very bright, right? Some may be interrupted because they painted a line, and then now 2 years have gone by, monsoons, it has washed out part of the line. So you might get a lower vote, but it's our job using heuristics to take that data and then pull out the lines that are most important for a car, which is these two. I don't care about a treetop line, so I can eliminate that, How is it possible I'm driving here and, the edge of the lane line is there, right? It's not possible. So, I'll show you some results now. So basically this thing, the same thing. Yeah, okay, I showed you, like, you see here? 1, 2, 3, and 4. They're all over the place. It can be any, number of MNCs. That is a Huff transform image. So the MNC, the voting, is converted to an image. Bright means that lot of voting for them. So this image, I don't know what the original image is. It has a lot of line structures. But I'll show you something that makes more sense. And then I'll show you the results from the 3 VIT students who got their PhDs, and of course, they did a CROSS project. It'll be very clear from it's still loading. No, that's not working. So you can pick out from the satellite view. You can pick out buildings. So you know that there's a lot of aerial surveillance for bombing. Maybe not the best use of human brains, but wars are cannot be avoided. They're going on all over. So basically, you can pick out a building and say, does it compare with the one where all the weaponry is kept? So Huff transform will pick out the outline from the satellite image, and then you can compare it to a map and say, okay, that's what I want to hit. So this was not what I wanted to show you, but we still had a good conversation around it. Maybe go back to the previous one. Yeah, this is the one. So all satellite photographs can be broken up like this into straight line structures. And then you can identify buildings and so on. So, a train, right? And I don't know what advantage, because a train is not a car. It is going to stay on the rail line, so I don't know what advantage will be gained by picking out the lane lines, but I think he's just doing an academic paper. He's trying to show that how transform works in this case. And see, the sun is there, so it's going to be a little bit difficult. Your camera, the sun is very low in the sky. So essentially, he grabs the picture and he's doing half transform on it, and there it is. See, he's able to even the interchange, he's able to pick it up. So once you get the strongest lines, you can make all the rest of it, black, and just show your strongest lane lines. And not only that, even those with gaps in it, remember the yellow line, maybe monsoon rain has washed out part of it, it can be made strong. Because once you're confident, you can physically draw a line through it. Yeah, that's what he's done here. See, the red overrides everything and makes it firm. And this, he tried it out in snow. I guess it didn't work that well. It seems to be slightly off. Instead of here, it's put it here. So those are the real world challenges, right? Nothing is perfect. Now, let me show you the first one. So this is a course project for one of the classes they took. So do you know what this is? Like in the parking lot, you sometimes have these cement blocks, which is very bad for smaller cars, because the smaller cars, they don't have the clearance to for the fender to go over it. So I have banked my fender multiple times. I had to have repair work done on that. So if you don't see it, you'll hear a crunching noise and you know what happened. It's too late. So the bigger cars, SUVs, won't have a problem because the tire will hit there. So these are the raw images that Melvin and Karthika used. So obviously you want that in order to prevent yourself from hitting it, like a imagined application, because you want to prevent damage to the car. Also, you might want to pick out the parking lot boundaries, the parking spot boundaries. If that's of interest, then you'll be looking in this direction. You'll say those lane lines have to be like this, whereas the cement block has to go across the screen. So these are their iPhone images basically. This is the input data they use in the project. Then we have another one. Now if you're wondering whether they painted the lines bright to make the job easy, no. The university had just then painted, like they basically laid new tar. So it's a beautiful contrast. So they were smiling, on that day because it made their project easier because nothing is faded because it was painted the previous day. Okay, now some grass enters the picture, raw image again. So some grass has entered the picture, right? Some grass, so that's a challenge. Where exactly? You see here? You don't know which is vertical and which is horizontal, and you really want to catch the vertical part of it because this is not going to hurt your car. Maybe you don't want to go there, but you definitely want to pick up where it goes up. Okay, and I think we have one more raw image and then the results. Yeah, so this is a different contrast. You can see there's grass, there's some pebbles lying around, and there is that cement that damages your car. Okay, and here's what Melvin and Karthika did. So this is the rough transform result. So you can see that it also picked up that, right? Our eyes couldn't see it, but it picked up the point where the horizontal meets the vertical. So now they were able to actually, you can calibrate an image for distance, and so they can actually tell as the car backs how far they are from that cement block. So you can, you can actually build that into an app if you want. I'm sure cars have it. This was a great project for a course that they did. So here's another one. Result. So there it missed. They used the green color for the top of that. The top of the flat part. So the back edge. So somehow it picked up glare here and it thought this is the edge, but you can see white there. And then it picked up red. Fairly good. And then this one, of course, no problems. Because it's all, contrast is so good, so it picked up the top from this side, green for the other top, and then here's one of the last two. It picked up the top, but it seems to be kind of shading over. So if you're looking this way, you can also pick up the. So as I said, it will give you a number of half lines. You can say I'm only looking for ones across the image, or I'm only looking this way, right? And the treetops, you can say there's no way, that can be part of the road, so I throw it out. So the final thing is not related to this, but I'm going to show you what the students accomplished during the time they were here. One small part of what they accomplished. So they're all working in industry with good salaries, over 100,000 a year. So I wanted to show you, we went to the University of Michigan for the robotics exhibition. And so Melvin and Karthika, they took whatever they were working on there and set up a demo. So let's start. First of all, we'll start with this. So that is Ratish and that's Melvin. So Melvin's project had to do with search and rescue robots, But these robots are not going to carry injured human being, but it's just a concept. He created a new system where communication was based on something called LoRa. So LoRa is a communication system that survives a disaster. Because if all the infrastructure, the Wi-Fi towers come down, LoRa will still survive. It's an international standard, LoRa, long range something. I forget what the expansion is, but it's meant to survive. So he used LoRa and basically created a set of robots that are platooning, convoying. So basically only the first one is driving. So you see 3 Pioneer robots. We can't use the turtle bot. It will not, he takes it across the grassy field and all that. The turtle bot will not be able to go there. So these 3 Pioneer robots, they're like 30-35 pounds, and 2 Jackal robots. So 2 different companies. And basically only the first one is driving, the others are following. So it's like a leader follower. And then he does experiments like, he puts the cardboard between number 2 and number 3. So basically it's like a tree falling, in a disaster area. If you have a tree falling and suddenly your leader is lost, then the follower becomes a leader. After a few seconds, it says, okay, I can't see the leader anymore. And then it goes independently to the destination. So his thesis was based on the search and rescue model. So let me show you the remaining pictures and then we'll be done. Here's all 3 of them. So the pictures are much better here than here because of the fuzzy screen. That's Karthika, Melvin, and that's one of our junior faculty, Michael Santoro. And they were at this robotics fair at the University of Michigan. So this is Anna, and that's a spider robot, if you can see. It has legs like a spider. And that's my colleague, Dr. Pollock, and basically is conducting an oral exam of a project. He looks too intense. Maybe he's had too much coffee. And that is one of our robots with a gripper mounted. So the project was to go find this red flashlight and pick it up. The red flashlight could be a bomb, for instance. So substitute for a bomb and you pick it up and go throw it to the trash. This is Amadou Kane, one of my other students. The same kind of arrangement, he's also doing the same thing, but you can see that it's got a gripper on top. So this configuration brings both the branches of robotics together. Because now, remember what you said, localization is easy for this. It's not easy anymore. Because once you put it on the base, it assumes the problems of the base. And this assumes the problems on the top. So their problems are now, they can cry on each other's shoulders. Because they've got each other's problems. Finally, I wanted to show you this, but for some reason it's not pulling up. I don't know why. Oh, by the way, this is our self-driving car. So the platform costs about $18,000. And in Europe they use this electric vehicle. In Europe they use it as a regular car. I would never drive that in America because when you're next to those 18-wheelers, you feel like you're going to die any minute. Because it's so light that any gust of wind shifts it in the lane. And so when you're right next to a 18-wheeler, what if the battery runs out? So many people in Europe use it. It's good for short distances, but I would not take it on the freeways. So we have 2 of those. The base platform is 18,000, but then you got to put sensors and everything in there. I hope you enjoyed the course. So I'll give the same advice that I gave the VAC group this morning. So one thing is that this model of teaching is going to vanish. Because there's so much stuff on the internet that nobody will want to listen to people like me, talking on for hours and showing PowerPoint. So I showed you some YouTube videos, but you should actually make a practice of living on YouTube in the future. Because with AI, no job is safe. I don't want to scare you because you're very young, you're heading into your career, but no job is safe with the way AI is coming on. So you'll have to teach yourself constantly. Teach yourself something that people can hire you for. And therefore, you have to go to the internet and learn to learn from the internet. So we will at the most be facilitators, meaning that we'll facilitate learning, we'll offer some commentary, but the material there is so much better than what we can create, right? So for me to be useful, I should start creating material like that, right? Because that's where the real learning is. At the most, you require somebody to walk you through some key concepts. So you have to be self-learners to survive the century in the sense that have a job for a lifetime. And the second thing, is the piece of advice is unrelated, and it is that try to get a job where at least part of it you find interesting. So I have the luxury of having a job that large parts of it I'm interested. I don't like grading papers, right? And I don't like certain types of students who are always complaining. But other than that, it's fun, right? So you have to try and find a job where at least part of it is fun. Because if you take a job for the money, after a while you'll hate even coming to work. And then your whole mind will degrade. So it doesn't matter how much money people give you, believe me. You won't like that situation. So if you're trying to find a job, you have to have money obviously, but there should be something that interests you, that makes you want to go to work. You shouldn't say, how am I going to pass these next 8 hours? I feel so terrible. Counting, the hours till it's time to go back. So we have, in our profession, we have that ability. Sometimes you stay late in the evening because you're working on something very interesting. You should try to find a job that makes you feel that way, at least for part of it. But don't let your boss exploit you. I'm not saying do the job for free just because you like it. So you have to find the money to live, but also find something interesting in the job you take.